Hey everyone, today I'd like to share one of my favorite problems with you all. It's a pretty short problem statement, so let's have a look. Let ABC be three distinct real numbers satisfying the following two equalities. A plus B plus C is 6 and AB plus BC plus C is 9. We are required to find the value of fraction part of A plus fraction part of B plus fraction part of C, where these curly braces represent the fraction part. Alright, so now looking at this, it seems like a more of a standard problem, except it's missing some information. Usually alongside these symmetric sums, we're also given the value of ABC. And then using that, you can kind of construct a cubic in A, B, or C, and you can find out their values. Or more commonly, you can use the identities in three variables to find out the sum of these guys, or basically any kind of combination of A, B, and C. But ABC is missing here. So that's why my first thought over here is to perhaps calculate an upper and lower bound on ABC and help determine it roughly using this information about A, B, and C being three distinct real numbers. Now how do I do that? Well, a thing to note here is that these two sums over here are cyclic and symmetric. So my first thought is that because they are cyclic and symmetric, no matter what order A, B, and C are in, whether it is A lesser than B lesser than C, B lesser than C lesser than A, the same analysis will apply. So that's why my first step is, without any loss of generality, I will assume that A is lesser than B, which is lesser than C. Secondly, cyclic and symmetric sums appear commonly in polynomials. The most common idea here is to use Vieta's formula to form a characteristic cubic whose roots are A, B, and C. Basically, I want to form a cubic whose roots are A, B, and C. That's it. So let me just do that. Let f of x equal to x cubed minus sum of roots times x square plus sum of roots taking two at a time times x minus ABC equals to 0. And this has three roots, A, B, and C. So we have a cubic over here which has three real roots, and we're required to find what condition will that impose on f of x. So let me just draw a rough plot to get an idea of what we're looking at here. So my graph is somewhat like this. At negative infinity, f of x is also negative infinity, so it will approach somewhat like that. It'll have a maximum, intersect, minimum, and then again tend to positive infinity as x tends to positive infinity. And these roots over here will be A, B, and C. Alright, good. So a thing to note here is that if the minimum is positive, then f of x will only have one root. And if the maximum is negative, f of x will again only have one root, which is this one. So that's why in order for f of x to have three roots, it needs to have a positive maximum and a negative minimum. So let's try imposing that condition. F dash x will be therefore equal to 3x square minus 18x plus 9. Correct? So that's why we will then obtain 3 times x square minus 6x plus 3. Sorry, this is 12, my bad. Minus 4x plus 3, which is basically factorized as 3 times x minus 1 times x minus 3. If we draw the wavy curve, we'll notice that the critical points are 1 and 3. Beyond 3, the function is increasing. Between 1 and 3, the function is decreasing. And before 1, the function is increasing. So let's see, that means that 1 over here will be the maximum and 3 will be the minimum. So let's mark that on our rough plot. 1 is the maximum, and over here 3 is the minimum. Now, we just discussed that thus f of 1 will be greater than 0. That means that 1 minus 6 plus 9 minus ABC is greater than 0. That means 4 minus ABC is greater than 0, or ABC is lesser than 4. Next, the minimum condition, which is f of 3 should be less than 0. Three cubed plus 9 into 3, 27 plus 27, 54, minus 6 into 9, 54. So therefore this entire thing becomes 0, whereas over here we have minus ABC lesser than 0, or ABC itself is greater than 0. So from this discussion we just established that ABC lies between 0 and 4. Alright, that's progress. We found the bounds that we wanted on ABC, an upper bound from f of 1 and a lower bound from f of 3. Now, my next idea over here was that since I know the value of a plus b plus c, if I can somehow find the value of GIF of a, GIF of b, and GIF of c from this cubic, then I will be done. All I'll have to do is subtract that from this equation to obtain this expression. Alright, so now how do I do that? What is GIF? GIF is ultimately just a sufficiently strong inequality that confines a number between two integers. That's how I've always viewed GIF, and that's how you should as well. Now, what is the best way of locating a root or confining it between two integers? Well, the best way for polynomials is to use the intermediate value theorem. In order to use the intermediate value theorem, let me just calculate the values of f of x at different values of x, like 0, 1, 2, 3, and so on. So let's notice f of 0 over here is minus ABC, so f of 0 will definitely be negative, which is seen in our graph here as well. I was lucky, I guess, drawing the graph. Next up, we know that f of 1 is greater than 0 because of the maximum condition. So f of 0 is less than 0 and f of 1 is more than 0. That means that the curve will have a root between 0 and 1 as dictated by the intermediate value theorem. We just determined over here that a is the smallest root, so let a be between 0 to 1. Alright, next let me try calculating f of 2. F of 2 is equal to 2 cubed minus 6 times 2 square plus 9 times 2. 9 times 2 is 18, 18 plus 8, 26. 26 minus 24 is 4, 4 minus ABC. So this is also indeed greater than 0. F of 2 is a positive number. So maybe f of 2 is somewhere here. And then we know that f of 3 is less than 0. That means that b, the second root, will lie between 2 and 3. Alright? So b lies between 2 and 3. Let us check what f of 4 will be. F of 4 will be equal to 4 cubed minus 6 times 4 square plus 9 into 4. 64 plus 36 is 100. 100 minus 6 into 16, 96. 100 minus 96, 4, 4 minus ABC. Which is again greater than 0. And we just saw over here from the minimum condition that 3 is lesser than 0. So the third root, C, will lie between 3 and 4. This is 4. C lies between 3 and 4. And we are done. All we did over here was calculate f at different values of x and determine its sign, and using that we located a, b and c within integral gaps. So we can accordingly also write their GIFs, like GIF a over here will be 0 because it is between 0 to 1, so the maximum value it can have is going to be lesser than 1, hence GIF is 0. B can be between 2 and 3. So GIF B is equal to 2. And C is between 3 and 4. So GIF of C is equal to 3. Hence, if we subtract this sum from 6, we will obtain fractional part of A plus fractional part of B plus fractional part of C is equal to 6 minus 0 minus 2 minus 3, 6 minus 5, or equal to 1. And that, ladies and gentlemen, is the required answer. Now, the strategy here was pretty obvious, I'd say. First, you find ABC because it was missing here. Next up, you want to determine the GIFs of A, B, and C so that you can subtract and get this expression. So in order to do that, you apply the intermediate value here. It's 2 steps. Let us see how we can maybe try out different things with the same problem. Maybe we could also try figuring out what would be the range of an expression a raised to power 9 plus b raised to power 9 plus c raised to power 9. How? Well, you could always use the identity a cube plus b cube plus c cube is equal to 3abc plus a plus b plus c into another factor, and therefore express the sum of 9th powers in terms of abc alone. In fact, if you try to do it, you'll realize that is a cubic again. And now what you have to do is that you have to analyze this cubic in the interval from 0 to 4. Because it's a cubic in ABC, and we've confined ABC from 0 to 4. So there are a lot of extensions you can again make to this problem, because we have some nice numbers here that let us confine A, B, and C between 2 integers. If they were different numbers, perhaps the ranges would have been bigger, and we might not have been able to determine the sign of f of 1, f of 2, f of 3, f of 4, and so on. So overall, I'd say that the strategy over here applies to this problem beautifully, and I'd encourage you to develop similar problems on your own. Thank you.